right. So far in this class, we've talked about analog circuits, and analog's neat, and we'll talk more about what the difference between analog and digital is, but I wanted to switch gears just a little bit and kind of show the direction we're headed with all of this electronic stuff and where it's all, why we cover this as chemical engineers. And this part of the course I know you haven't had in physics or in your circuits class probably. So it's something I want to show you because not only does this exist as an electronics thing, there are digital circuits for pneumatic systems, digital circuits for hydraulic systems, and so on. And so the logic here and some of the stuff I'm going to cover is not just tied to electronics, but tied to other aspects of engineering. So first thing I really want to get clear with everybody is how to deal with binary. And why I have this is, if we think back to when we were learning to count, we probably didn't start learning to count with 0, but oops. If we had, what we could do here, I'm going to switch over to a pen here. So we notice we've basically got, when you were first learning to count, you've got a ones place and a tens place, right? And our possible digits for any of these are 0 through 9, right? 0 through 9. So what happened is we started out, and pretend we started counting at 0, and have to do that because we're dealing with electronics. Or, I mean, I'm sorry, we have to do that because I want to show 0, 0. So we got 0, 0. If I add 1, I get 1. Add 1, I get 2. Add 2, 1, I get 3. I add 1, I get 4. And so on. Basically, I keep incrementing the ones column. And it keeps going. You didn't take this course to learn how to count. But then we get all the way down here to 9. And what happens? Well, there's no digit after 9, so we restart. We started at 0. But we go ahead, and now that we've gone from 9 to 0, we know to put a 1 in the ones, or I mean, we know to put a 1 in the tens place. And the same thing goes, we get to 99. We try to add 1. Well, there's no more numbers after 9, so that has to become a 0. No more number, then we add those, and there's no more numbers after 9, so we add a 0. We go to 100, and so on and so forth. And that's because we have between 0 and 9 available to us. Now, in the computer world, we really only have 2 digits. We have 0 and 1. And the reason for that is basically a transistor is either on or it's off. And if you think about the power logo on a lot of your stuff, you know, on your computer and such, it's a 1 and it's a 0. That's where that comes from. In the old days, they used to have a switch and it looked like that, and you flip the switch between 1 and 0. So, if we only have 1s and 0s available, we count the exact same way. We start out, and we've got all these zeros. I'll explain that in a little bit. So, we start at 0, 0, 0, 0. We add 1. So now we have 1. But then when we go to add 1 right here, because our only possible digits are 0 and 1, we reset this one. So it's a 0. But we carry 1 over to the 1's place. Now, what's different from counting in base 10 versus base 2 is, of course, every time we have this transition where we try to add 1, moves over another place. So we go all the way through, and maybe we only have 4 transistors. That's why we have these 4 switches. What happens if I add 1 to that? Well, this one becomes a 0. 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 And if I don't have another transistor out here, that's it. We've accidentally reset our counter. So I'll talk more about that later on. But I just want you to see that. And I kind of explain all that through here. You can read through this. Sometimes you'll see these other ones. Base 8 is just 0 through 7. Base 16, you're like, what is that? Well, 0 through 9, A through F. And sometimes if you crash your computer, it'll say something like, there'll be an error, and it'll be like 37A to B4. And you're like, what is that? Well, it's some sort of hexadecimal number. Don't worry about that for now. Just know that there's other bases out there and other systems you can use to count. So there's some instructions here. You can read through it in case you didn't watch this video all the way. It tells you how to convert to binary, but I'll work through this example instead. And I've worked it out, but I'll work it out over here. So suppose we have the number 47. I want to find the biggest power of 2 that goes into 47. And so it helps to think about powers of 2. You learn to count in powers of 2 really quick. We know that 2 to the 0 is 1. Anything to the 0 is 1. 2, 4, 8, 16, 32, 64, and so on. So 0, 1, 2, 3, 4, 5. I'm going to choose 32. 2 to the 5th is 32. So I'm going to choose that. So I say 32. We can look at this and say, okay, we know there's at least 1 2 to the 5 in there. Next step is I subtract. And I get 15. And then I just repeat this process. And I say, well, 2 to the 5 doesn't fit anymore. That's good. That's what we took care of. 2 to the 4 doesn't fit because that's 16. But 2 to the 3 does. But since 2 to the 4 didn't fit, we can put a 0 in. But a 2 to the 3 does. So we'll put that in. 8. Okay. 2 to the 3 doesn't fit anymore. In this, in the 7 here. 2 to the 2 does, so we subtract out a 4. 2 to the 2, or 2 to the 1 does. Left of the 1. 2 to the 0 does, because 2 to the 0 is just 1. So we can say that these are equivalent. Going the other way, we can take a number like this, and we can say this is the 2 to the 5th, 2 to the 4th, 2 to the 3rd, 2 to the 2nd, 2 to the 1st, 2 to the 0. And I can basically just add these up. 32 plus 8 plus 4 plus 1. So we can convert back. So there's, I think, a homework problem where it talks about converting to and from binary. And why we do this, like I was saying earlier, is computers really only understand on and off or true and false. So that's the whole reason we're going to base an entire logic system on just true and false. So there's these ways we can deal with these ones and zeros to make actual decisions, and these are called logic gates. And while these logic gates exist and we can make all of them, some of them are a little bit easier to make electronically, to actually imprint on the chips and to actually use. So while all these gates exist, they're not, some of them are a lot easier to come by. And what I mean by this is, here's some different logic gates. And what this means is, suppose I had a NOT gate. If I were to apply a true signal to it, I'd get a false signal out. If I were to apply a false signal to it, I'd get a true signal out. That's how that works. It basically just, whatever we put in, it gives us the opposite. And I wanted to talk about these guys, and an OR, because in our language, we use them interchangeably, and they're not interchangeable. An OR means if any input is true, the whole thing is true. So if I were to put a 1 or a 0, it says if any input is true. Well, one of them is true, so there we are. But instead, if I were to use an AND, this one says if both inputs are true. So if I put a 1 and 0 here, that output would be 0. So these, even though we use them in our language interchangeably, they actually end up being different. And in fact, if you are, this isn't just related to electronics. If you decide you're done with chemical engineering and you want to go be a lawyer, if there's a contract and it says or, you need to do this, this, or this. If you've done any of those things, the whole contract is good. But if it says you need to do this, this, and this, and you do two of them but not the third one, you have violated the contract. So, these words have a specific meaning. Outside of those, so not or and, I think we have pretty good understanding of how those work. We can represent each of these algebraically too, where A and B are going to be our inputs, and X is like our result. So, and you could think of this a little bit, the reason we were chosen, like, hey, if I did 1 or 0, I get a 1. Hey, look at that. If I did 1 and 0, that whole thing would be 0. Just to help you remember that. There's some other gates, though. For instance, this NAND gate is very common. And what it does is we take whatever we got. It's like we've put these things together. In fact, that's exactly what we've done. So it's an and attached to an or an and attached to a not. So whatever we get out of here, we turn around and flip it, and we get the opposite on the output. And the reason I put NANDs up here is this is a really common gate to make. This is really easy. Well, I would say easy. You need a semiconductor plant, but it's one of the more common gates out there. And so you'll do some stuff with that in your lab. Some of these other ones, like not exclusive or, this is an exclusive or. Exclusive or means one and only one. Well, there's one and only one input is true. And if we take the opposite of that, that's a not exclusive or. So there's all these different gates. They all exist in theory, and you can use them for different things. So just as examples, I kind of went through the and or and the not. True and false is false. True or false is true. If it's not true, it's got to be false. This isn't politician land. You have to pick one or the other. So, suppose we have a piece of equipment and it has an emergency stop button. And we want to see when to stop the machine. So we've got an emergency stop. We're going to call that input A. It also has an interlock. And what I mean by an interlock is sometimes on big pieces of equipment you put a mechanical switch so that if you go and rip a panel off of it or open something you're not supposed to, it just goes ahead and kills the circuit. It just knows that you're not supposed to be there, so it shuts down. So, if we want to stop the machine, obviously, if the emergency stop button is pressed. We may also want to stop it if this interlock is open. So we'll call that input B. But we want to be able to stop it if either one of those things happen. So we can say, well, if A or B, if somebody presses the emergency stop or opens the panel, we need to be able to stop the machine. And we can kind of reason our way through this. And wouldn't work. This would not be the good option, because if this were happening, to stop the machine, we'd have to simultaneously hit the emergency stop button and kick some panel out, which might happen or it might not. If it does, the or still works, but it would be the only way to stop it if we used an and statement. So you can kind of reason your way through a simple one like this, but as things get more complicated, it gets a little harder. Like, how does this behave? And now I've got this third input, and then this is not A and B, or B and C. How do we deal with that? And so what we got to do is we got to go through some steps. We're going to build a thing called a truth table and figure out how to work out what the outputs are going to be. So right away we see we've got an A, we've got a B, and we got a C. Those are our three inputs. And we're getting an X output. So first thing we got to do is find our possible inputs. Then we're going to break this whole thing down into sections and look at each piece. And this is all going to be compiled into a truth table. So what do I mean by all this? Well, finding our possible inputs. We've got an A, which is either a 0 or a 1. we've got a B. It's either a 0 or 1. I got a C that's either a 0 or a 1. And what I've done here is I've listed all the possible combinations of A, B, and C. And if you don't want to try to figure that out, I mean, the possible number of combinations is 2 to the n, where n is just 1, 2, 3. If you don't want to list them all, or if you don't want to do this, one way you can figure out what combinations are there is to just count until you've basically start at 0, 0 and end up at 1, 1, 1. So I added 1, I added 1, I added 1, I added 1, and so on. Now what we do is, okay, we list them out as a table, A, B, and C. Those are our 3 inputs. And if you notice, we've got our 3 numbers here. I should also mention, so like, if we were to work through the binary conversions, if we just count, we'll see that it's 0 through 7 in this case. So, same thing over here. We got 0, 0, 0, 0, 0, 1, 0, 1, 0. Basically divided those into columns. So the first step of this, I'm going to look at this not A. Well, all I do is I take these guys over here and I not them. So not 0 is 1. Not 0 is 1. Not 0 is 1. You know, you get the idea. Not 1 is 0. Not 1, 0. Not 1, 0. Okay, so we got our A not. Or not A, I guess I should say. Then I want to look at, what about not A and B? So I take these, and I say 0 and 1. Well, that's 0. 0 and 1, 0. 1 and 1 is 1. 1 and 1 is 1. 0 and 0 is 0. 0 and 0 is 0. 1 and 0 is 0. 1 and 0 is 0. Okay. So now we've got that part. Now we can look at, and B, C, C, B, same thing. I can take these 2 columns and I can go through and just AND them. 0 and 0 is 0. 0 and 1 is 0. The only time I get a 1 is if they're both 1s. So there's an example where they're both 1s, and there's an example where they're both 1s. So then the final column here, I could basically take that and that, and we just put an OR between them. All right, 0 or 0 is 0. You know, so that's boring. 0, 0, 0. 1 or 0 is 1. 1 or 1 is 1. 0, 0 or 0, 0. 0 or 1 is 1. So that's how we can basically build these tables. So we can look at a complicated equation and break it into something that makes a little more sense. So one thing you can think about is, if you have an alarm clock, it's got this 7-bit or 7-segment LED. And you know that each of these only comes on when it's the right number. So if I want the number 7, it's like those 3 come on and none of the other ones. And so each of these is like a little logic output. And so how many bits are needed to represent 0 through 9? Well, I've got basically 0 through 9 combinations. So I need, well, let's see, 2 to 0. That only gives me one option. It's either on or off. Or I mean, that's a poor example. Get rid of that one. 2 to the 1. That gets me 2 examples. It's like so a bit, I should back up. A bit is like one of these little switches. It's either going to be a 1 or a 0. And so if I only have one of those bits, I only have 2 options, on or off. So that could only represent 2 numbers, on or off. Or 1 or 0 or something like that. If I have 2 bits, where this is just n, this is our number of bits, now suddenly I have 4, because I can do 0, 0, 0, 1, 1, 0, 1, 1. Well, I need to represent that many. I need to represent basically, sucks that I have to do a 10, but basically I have to have 10 possible states. You could call it that. And so 2 to the 4 doesn't work, because 2 to 2 doesn't work because that's all the possible options. That's only 4 possible states. So 2 to the 3 Now I got 8 possible states. And while it's close, it's still not 10 possible states. So I have to go all the way to 2 to the 4, which is 16. Now, in order to represent 9, 0 through 9, I basically have to have 4 bits, and that gets me above the number of states I need to represent. And some of these states aren't going to be real values, they're not going to be 0 through 9, they're going to be something else. But that's okay. And so what we can do is we can look at this A here and say, okay, when does it light up? Well, lights up when there's a 0. Lights up, doesn't light up when there's a 1. Lights up when there's a 2, lights up when there's a 3. Doesn't light up when there's a 4, does when there's a 5, does when there's a 6, done when there's a 7, done when there's an 8, done when there's a 9. And we can do that for every one of these. And there's this thing called a Carnot map, and I just throw the term out there, so if you get into this, you can start looking and learn a little bit more. But there's ways you can simplify this so that you can figure out when these are lit up. Well, where all this is going, we could write out logic statements for each of these segments, and then we could build an entire circuit around it. Now, thankfully for you, we're not going to do this, but there's our 4 spots. So if I put a 0, 0, 0, 0, and wanted that to represent, the digit 0, we could work through this, and, certain things would be flipped and certain things wouldn't, and we would light up this as a 0. So that's where this is going. This is what goes into every digit on your, say, alarm clock, which nobody carries anymore. Everybody's got a phone. Nobody uses an alarm clock anymore, but you get the idea. That's how you create those. And so you can imagine if you had to build all these out, that's a lot of little chips. Well, or that's a lot, you've got a couple little circuits in your kit, have these little pins, and maybe this one goes to VCC, which is power. It's going to be 9 volts for you. Maybe this one goes to ground. And maybe inside of that chip you have a NOT gate, and maybe you got a couple of them. And so on. You could imagine that this is going to take a bunch of chips. Thankfully, we can do this much smaller than those chips you're using. Those chips you're using some of that is 40-year-old technology, and it's done so that you can learn the concepts. This whole chip, this whole programming here for 4 switches to an LED controller would fit. Many of them would fit in a spot that big if we wanted them to. So just wanted to throw that out there. That's kind of where we're going, and don't worry if you don't understand all of it yet. We'll spend a little time on it, and you'll get to practice some of this in lab. So that's what I've got. Thank you.